Okay, so this is our first video covering the material from Chapter 3 for Math 1560, Calc 1 at U of L for Fall 2017. In this video we're going to look at the extreme value theorem. So the extreme value theorem is similar to the intermediate value theorem, and not just because it has two of the same words, but it's another one of these results which is kind of obvious if you think about it, but also very difficult to prove. Now, before we get into the statement of the theorem, we need a little bit of terminology. So we need to talk about absolute or global maximum and minimum values. In the textbook, you'll find the word absolute. Other books will use global. I tend to bounce back and forth between the two, so you'll just have to get used to hearing both words. So an absolute maximum value is the largest value that your function attains on its domain, right? So it's the biggest value that you get. And the absolute minimum value is the smallest value that you get. And now, by the way, these are not necessarily guaranteed to exist, but if we look at this basic example, we can see that you do indeed get an absolute maximum and minimum value. Just think of plotting this thing. So here's some axes. X equals -1, 1, 2. So what do we get? We get something that looks like that. This point over here is the point 2 and then 2 squared, so 2, 4. Over here we've got -1, 1. Down here, of course, that's the origin, 0, 0. And we can see that for this particular example, the absolute maximum is going to be at 4. That's the maximum value, and that is attained when x is equal to 2. The absolute minimum would be 0, and that's attained when x equals 0, right? X squared is never less than 0, so that's the lowest we can get, right? So the biggest we get on that particular interval, and then the smallest we get, right? Now, of course, if I modified this and said, well, instead of looking at the interval from 1 to 2, let's say I want to consider the whole real line, right? Well, if I consider it on the whole real line, then there is no limit to how big my function can get, right? And so the max just would not exist in that case. There would be no maximum because it keeps getting bigger and bigger and bigger forever, right? And there are plenty of other ones where you see similar behavior. If we looked at, say, g of x equals 1 over x, if you plot that, right, this hyperbola goes like that and like that, right? There's no minimum or maximum in this case, right? It goes off to plus infinity in one direction, minus infinity in the other direction. Or even if you had something which, just kind of went down but then kind of ended at an open interval, right? And you never quite reached that point, well, then there wouldn't be a minimum value because you can get closer and closer to that point that's missing, but you never actually reach it. Okay, so when can we be assured that these values exist, the maximum and the minimum? Well, that's what the extreme value theorem tells us. So the extreme value theorem says that if we have, and let me highlight the key points here, if we have a continuous function on a closed interval, then it's guaranteed to have a global maximum and a global minimum, right? So you're guaranteed that you'll be able to find one point in the interval where you get your maximum and another point in the interval where you get your minimum, right? And continuity is essential here, like we saw in those examples, right? If we went with, say, A, B, and we start here, maybe we end over here, right? Well, maybe my graph goes something like this, right? So I'm looking for the max and the min. Where's the minimum? Well, what's the smallest value we see? It's down here, right? So here would be my D, right? Here's my absolute min is happening down here. Where's the maximum? it's up here, right? So the absolute maximum actually happens to occur, in this case, at one of the endpoints. Right, so, and that can happen, right? So it might be that you get a max or a min because the function dips down or shoots up, but it's also possible that that max or min value happens at one of the endpoints. But we are guaranteed, the extreme value theorem does guarantee that these values exist. So as long as we know that our function is continuous and our interval is closed, then we can go looking for these points. And we'll talk about how to find these points in some later videos. Now, just to give you some examples to show you that the assumptions you're making are essential, let's look at what happens if we did something like, let's say, one where f is continuous, but we're dealing with an interval that's not closed. Well, there's an easy example there. Let's take the natural log function, right? So the natural logarithm is continuous on its domain, right? But what's the domain? 0 to infinity, right? This is, we know that there's no max and there's no min, right? Because what does the graph look like? The graph looks like this, right? The y-axis is a vertical asymptote. It goes off to minus infinity, so we don't get a minimum value. And if we do let it go off to infinity, then we don't get a maximum value either. Now, and even if I change this, if I change this to say, well, let's not go to infinity, maybe we say, hey, let's go to let's go to maybe, I don't know, 10, right? And somewhere out here is 10. Well then, but we don't include 10. Right? If that happens, then my graph gets closer and closer to that point where x equals 10, but I never quite reach it, so I don't actually attain that maximum value. On the other hand, if I were to change this and go to a closed interval, like so, well, then I get to fill in that point, right? And then that would be my maximum. My maximum would happen at that endpoint, but I still wouldn't have a minimum. Right, so it depends on what you're looking at there. Similarly, if I had a maybe the interval is closed, but f is not continuous, well, there are plenty like that. In fact, we just saw one, right? We could say something like f of x equals 1 over x. We could go from -1 to 1. Well, my function is not defined at 0, right? It's not continuous on the entire interval. I have a discontinuity at 0, and so the extreme value theorem fails. Or even if just kind of graphically, I could have something like this, right? I could go from A to B, and maybe I start here, and I head up, and I don't quite reach that point, and then I have a jump, and I come down to here, and then I go down, right? I could have something that looks like this, where I do have a minimum. I would have a minimum down here, but I don't have a maximum because I never quite reached that point. So I'm not guaranteed existence of these values if either of these two assumptions, either the continuity of the function or the closed interval, if I don't have one of these, I might still have a max and a min, but I might not. There's no guarantee. So in the cases where these values do exist, in the next couple of videos, we'll see how to go about finding them.